This lecture is on infrared spectroscopy and mass spectrometry. In order to understand infrared spectroscopy, we first have to look at some fundamentals. First, what is infrared or IR? Infrared or IR radiation equals heat, which is lower in frequency than red in the visible spectrum. We can't see heat. We can only see the red part of the visible spectrum, and below that we have infrared. Pit vipers, a kind of snake, can actually see heat, which is how they're able to find their prey in the dark. If you look at that spectrum below, you can see that IR is on the right, which is just below the red. Now, bonds and functional groups can be detected by the frequencies of IR radiation that they absorb. That's how we use infrared spectroscopy. Bonds act like springs. They can stretch, and for two or more bonds attached to the same atom, they can bend. These are the vibrations or vibrational modes. For formaldehyde, I'm showing you the C double bond O stretch below and the CH2 scissor bend, where the two CH bonds work together to create a scissor-like bending vibration. Well, we just saw a couple of vibrational modes for the molecule formaldehyde. IR radiation absorbed by a molecule matches the frequency of that vibrational mode. IR radiation is only absorbed if the dipole moment mu changes during a vibrational mode. So, for example, if you look at acetone, the CO stretch changes the dipole moment, because the distance between the partial positive charge on carbon and the partial negative charge on oxygen increases during the stretch, and then decreases when the oxygen snaps back toward the carbon. That change in the dipole moment allows infrared or IR radiation to be absorbed. If you look at the example of acetylene, the C triple bond C stretch will not cause a change in the dipole moment. We start off with zero dipole moment, and we end up with zero dipole moment. Since mu doesn't change, the bond dipoles still cancel. There's no IR absorbed for C triple bond C, and thus in this molecule you cannot use infrared spectroscopy to detect C triple bond C. It does not absorb IR radiation when that stretching mode occurs. Stretching modes are higher frequency than bending modes because they're harder to do. It takes more work to stretch a bond than it does to bend a couple of bonds toward each other. The stretching modes are useful for matching IR frequencies with functional groups. So that's how we'll be using stretching modes. We'll be using those to detect functional groups. IR frequencies equal wave numbers, which is reciprocal centimeters, centimeters to the -1. We get that from taking the frequency, which is seconds to the -1, or 1 over seconds, and dividing that by the speed of light, which is centimeters per second. We take those two terms and divide them. We'll end up with centimeters to the -1. This is the x-axis of an IR spectrum. And the reason that we do this is that if we don't, and we use actual frequency units, they'll be huge, and they're kind of cumbersome to put on x-axis. So instead, we simply divide by the speed of light to get smaller numbers. The y-axis is percent transmittance, which is how well the infrared radiation is absorbed by the substance. Starting at 100% at the top of the y-axis, where there's no absorbance, down to 0% at the bottom, where the substance completely absorbed infrared radiation at that frequency. So we're going to see peaks. They're going to go from the top to the bottom. They're going to make a dip. Let's look at the key features of an IR spectrum of acetone. Right off the bat, at the highest frequency, there's a water impurity. This is exceedingly common for very polar organic substances like acetone, which absorb water. So we ignore that. In part A, we have a stretching frequency for the CH stretch. That's around 3,000 wave numbers. And in part B, we have a really intense stretch for the C double bond O bond, and acetone. These would be considered to be the stretching modes for functional groups in the acetone molecule. The alkane portion in A and the C double bond O or ketone portion in B. The IR spectrum below 1500 wave numbers is called the fingerprint region. Since here you can match the peaks from an unknown substance with all the IR spectra of known substances in an IR spectral database to identify an unknown substance, for example a poison. This is very useful for forensic analysis, such as at a crime scene where a murder may have occurred and you think there might be a toxin that caused the murder. However, what you're going to try to do is figure out the structure of a chemical substance that's pure, not compare your infrared spectrum to an entire database. So we're not going to be using that region below 1500 wave numbers. It won't be particularly useful for you. Your job is to figure out possible molecular structures from an IR spectrum. So with a few exceptions, you only care about IR peaks above 1500 wave numbers. Now you're going to need a table of functional groups and the IR frequency ranges that match them. This is called an IR correlation table. Click on the link in the video description to get one on a separate web page to solve practice problems in this video. Now when you look at an infrared spectrum, some peaks are big, some peaks are really small. Now the tiny peaks, which are less than a 10% drop in transmittance from the highest transmittance value, are generally ignored. Those are probably just impurities or some very tiny artifacts in the infrared spectrum. So only look at peaks which drop greater than 10% below the top transmittance measurement in your infrared spectrum. Here is the IR correlation chart that you'll see if you click on the link in the YouTube video's description. There are three important columns: the functional group name with the IR absorbing bond in parentheses, the structure with the IR absorbing bond in bold, and the IR frequency range in wave numbers. So at the very top row we have alkanes, where you have the CH absorbing bond. There's its structure, and the frequency range is between 3000 and 28 wave numbers. Very common in all infrared spectra will be this CH stretch, so you usually aren't going to pay much attention to it because this is organic chemistry and you're going to see CHs all the time. Under that we have alcohols, the OH stretch. This is a peak or band which will be very broad. So that's going to stretch, the band will actually extend between 3600 and 3200 wave numbers. So we're talking about something which looks exceedingly wide, not like a little dagger. Then we have the amines, which can be of two types. You have NH or NH2. This could also be attached to a C double bond O for R, which would make it an amide. And in the case of NH, that gives us one band between 3500 and 3300 wave numbers. But in the case of NH2, we have three bands. Two bands between 3500 and 3300 wave numbers. And that's because the NHs can either stretch in the same direction, both stretching outward and in at the same time, or one could stretch out while the other stretches in. So that gives you two different bands. And then we also have the bending vibration, where the NHs are doing that scissor-like bend that we saw before, where they're slapping together like two parts of a scissor closing. And that's between 1650 and 1560 wave numbers. In order to confirm that you have an NH2, other than of course there must be a nitrogen in the molecular formula and sufficient hydrogens, you must also show that there are these three infrared peaks in the infrared spectrum. Two bands between 3500 and 3300 wave numbers, and another one between 1650 and 1560 wave numbers. Another example of a functional group which can only be determined if you have more than one peak detected is the carboxylic acid. With the carboxylic acid, you have the OH stretch, very broad, between 3200 and 2500 wave numbers. But you must also have the C double bond O stretch, which, if you look down at the bottom of the chart, is between 1765 and 1680 wave numbers. Now, here's an important overlap area in terms of IR frequency ranges, and that's for the alkyne and the nitrile, C triple bond C at the top right, and C triple bond N just below it. C triple bond C absorbs between 2260 and 2100 wave numbers, whereas C triple bond N absorbs between 2260 and 2200 wave numbers. So most of the frequency range overlaps for these two functional groups, making it very difficult to distinguish which one it's going to be in an infrared spectrum. So when you detect that a peak or a band in that region, you just say to yourself, well, I either have C triple bond C or C triple bond N. And you let other information about the molecule, the presence of a nitrogen, and other structural features, other infrared data, narrow down the possibilities so you can determine whether or not you have C triple bond C or C triple bond N. Just having a peak in that region will not tell you which one it is. Here are the steps for determining possible molecular structures using a molecular formula and an IR spectrum. First, given the molecular formula, you have to calculate the number of degrees of unsaturation, or DOU. Remember, the DOU formula is number of carbons plus 1 minus 0.5 or a half times parentheses the number of hydrogens minus the number of nitrogens plus the number of halogens end parentheses. If there is unsaturation, look for pi bonds in the infrared spectrum, such as C double bond C, C double bond O, etc. Okay, you're going to need to do that first so you can determine that these pi bonds exist, and you draw those down right off the bat. Be careful about specifying what kind of C double bond O you have, since there is a lot of frequency overlap for C double bond O containing functional groups. Only be specific about amides, anhydrides, and acid chlorides. With a DOU greater than or equal to 4, and 2 to 3 peaks between 1600 to 1450 wave numbers, there's probably a benzene ring, which has a DOU equal to 4, because it has 3 pi bonds and a ring, with a total of 4 DOU. Find all other functional groups, such as OH, NH, or NH2, and that C single bond O functional group, which is sometimes tricky to find. It's between 1000 and 1300 wave numbers in the fingerprint region. It's not always the most obvious unless there's really nothing else going on, and sometimes it overlaps with other bending vibrations. But if it's a very simple molecule, such as an ether, you'll be able to see it easily. To confirm the presence of a functional group, you must find all of the required IR peaks. For example, in the carboxylic acid, as we mentioned, you have to have both a broad peak between 3200 to 2500 wave numbers per OH, and a second peak between 1765 to 1680 wave numbers. Always make sure you find all of the required IR peaks for the functional group. You can't have some. Some's not enough. Draw what you found and subtract those atoms from the molecular formula. You should be left with only single bonds connecting all the functional groups and remaining atoms. If you need more unsaturation, okay, but you don't have any more pi bonds, then make rings, 3-sided, 4-sided, etc. So what you want to do is draw all the possible structures that fit the functional groups that were detected in the infrared spectrum and fit the DOU. Practice problem 1. Determine 2 possible structures, unless only one structure can exist, with the molecular formula C4H6O and the following IR spectrum. There's a water impurity, so you want to ignore this. And remember to use the steps that you saw in the previous slide which include calculating the degree of unsaturation. Answers to practice problem 1. Using our degree of unsaturation formula, we can calculate that DOU equals 2. There is a C double bond O peak between 1750 and just below 1800 wave numbers. There is no C double bond C, because there's no peak between 1600 and 1680. So, given the formula, which only has one oxygen, there aren't two C double bond O's. Thus, there must be a ring in addition to C double bond O to give us a DOU of 2. There is a CH around 3000 wave numbers, but that's of course commonplace for organic compounds. In conclusion, we have a couple of structures we can draw which have a C double bond O and the additional unsaturation, which must be a ring. And those are shown on the right. These are not the only possible structures that you can draw. For example, instead of drawing a ketone, you could have drawn an aldehyde connected to a three-sided ring. In mass spectrometry, unlike infrared spectroscopy, we're not looking at how the molecule absorbs any kind of radiation. Instead, we're looking at the mass of the molecule, and if that molecule falls apart into different pieces, we're looking at the masses of those pieces, and we're looking at that information to figure out the molecular formula and often the structure of the molecule. If our substance isn't already a gas, in order to analyze it by mass spectrometry, we must first convert under very high vacuum the solid or liquid substance into gaseous molecules. These gaseous molecules then collide with high energy electrons to form radical cations. The molecular ion M+ dot is a radical cation. The unpaired electron makes it a radical, the plus charge makes it a cation. Excess energy from the collision makes the molecular ion break up into fragments unique to the molecule. So for example, with CH4 plus dot, that's the molecular ion for methane, we can either break up into CH3 plus and a hydrogen atom, or a proton and a CH3 radical. The detector in a mass spectrometer amplifies current. Now, current requires moving charged particles. These can either be cations with a plus charge or anions with a negative charge. Thus, only the cations are detected in the example shown, where the methane molecular ion, which can be detected because it has a plus charge, breaks up into the CH3 plus cation, that can be detected, and the hydrogen atom cannot be detected. Alternatively, the methyl radical cannot be detected, but the proton can be detected. The x-axis of a mass spectrum is atomic mass divided by charge, or m/z, and z is usually +1. The y-axis is relative intensity, 100% at the top to 0% at the bottom. So all of the peaks that you'll see in a mass spectrum are going to be lines that correspond to specific mass-to-charge ratios along the x-axis and have a certain intensity that is shown on the y-axis. Mass spectrometry easily detects stable, significant isotopes in a sample of molecules. So for example, with methane, not only do you have C12, H4, where H has one proton as the molecular ion with a mass-to-charge ratio of 16, but you also detect the C13 isotopic version of methane with a mass-to-charge of 17, although it's only 1.1% abundance relative to C12 methane. Here we have the mass spectrum of methane. At mass-to-charge ratio of 16, we have the molecular ion, where we have carbon as the 12 isotope, the most abundant isotope of carbon. And right next to that at 17 we have the M+1 peak with the carbon-13 isotope. Then below 16 we have one major fragment, which is for CH3+, and that's again with the carbon-12 isotope. There are a few other fragments with lower mass-to-charge ratios, but they're less common. This would be due to the loss of hydrogen atoms from CH3+. Of the two peaks at the highest mass end, the most intense peak is the molecular ion. Now we're talking about peaks that have at least 1% abundance. You have really tiny trace peaks that are below that, which may be slightly higher mass. We're just going to ignore those. Isotope abundance ratios help to determine the presence and number of atoms of a given element in a molecule from its mass spectrum. So for example, if you compare C12 to C13, that's about 100 to 1.1 for the M to M+1 peak. That's with one carbon atom present. For bromine 79 to bromine 81, the ratio is about 1 to 1, which would be for the molecular ion compared to the molecular ion +2, or M to M+2 peaks. That's with one bromine atom present. And for chlorine 35 versus chlorine 37, the ratio is about 3 to 1 for M to M+2, again with only one chlorine atom present. For example, given the C12 to C13 ratio is about 100 to 1.1, and the proton, H1, is the only significant isotope of hydrogen, we can figure out how many carbons there are in a hydrocarbon. So a hydrocarbon with an M to M+1 ratio of 100 to 6.6 should have 6 carbon atoms. How do we figure that out? Well, we take the 6.6% and we multiply it times the fact that there are, for one carbon-13 atom, 1.1% abundance. So 6.6% times C13 atom per 1.1% abundance gives us 6 carbon-13 atoms, which is of course the same as saying that there are 6 carbon atoms present in the molecule. We're not saying that all 6 carbons are going to be carbon-13. That of course would give us a much higher mass. We're saying that there is a 6.6% chance that any one of those 6 carbons could be carbon-13, because there's a 1.1% chance for each one. Multiply times 6, that's a 6.6% chance. An odd mass molecular ion has a very important distinction. It means an odd number of nitrogens are present in the molecular formula. Even mass molecular ion means no nitrogens or an even number of nitrogens. So for example, a mass spectrum has a molecular ion with a mass-to-charge ratio of 41. And the M to M+1 for this compound is 100 to 2.2. There has to be one nitrogen. It's an odd mass, and 3 nitrogens, which was also odd, would be 42 atomic mass units, and that's too much. There also have to be 2 carbons. We've got 2.2% for the M+1 peak, which when multiplied times for 1 C13 divided by 1.1%, we get 2 C13 atoms, or 2 carbon atoms. To get the molecular formula, subtract the masses of what you found, and the rest are hydrogens. So we have 41 minus 14 for the nitrogen, minus 24 for the 2 carbons, equals 3 remaining hydrogens. The molecular formula is thus C2H3N. We always write, for organic compounds, the molecular formula as the number of carbons, then the number of hydrogens, followed by the rest of the elements in alphabetical order. Now, if you don't know the M to M+1 ratio, subtract the masses of what you do know from the IR and mass spectra, and assume the rest are carbons and hydrogens. Divide by 12, that is the mass, and the remainder is hydrogens. So for example, a mass spectrum with an M to M+2 ratio of 3 to 1 has a mass to charge of 50 for the molecular ion. There must be a chlorine atom present, because it's a 3 to 1 ratio for M to M+2. Subtract 35 for chlorine 35 from 50. You do that, you get 15. 15 divided by 12 equals 1, dividing evenly, and the remainder is 3, which is for 3 hydrogens. Thus, the molecular formula is CH3Cl. Note, if your molecular formula seems nuts, this doesn't make any sense, because it gives you a DOU, which is the same as the number of carbons in your molecular formula. Subtract 1 carbon and add 12 hydrogens to get a reasonable molecular formula. For example, C7H2 has a DOU of 7. That's pretty crazy. So instead, we write C6H14. We took away one of the carbons and we added 12 hydrogens. Now we have something with a DOU of 0. Practice problem 2. Determine the molecular formula and 2 possible structures, or 1 if only 1 is possible, of a compound with the following IR and mass spectra. You have to use all the information you have about isotope abundances, right? Like the M to M plus 1 ratio, which tells you how many carbons there are, and the M to M plus 2 ratios, which can tell you whether or not you have a bromine or chlorine present. Also remember that for odd mass molecular ions, that means you have an odd number of nitrogens. Answers to practice problem 2. In the mass spectrum, we have a bromine atom present because the M to M plus 2 ratio is about 1 to 1. For the master charge of 120, which contains bromine 79, and the master charge of 122, which contains bromine 81. Now, in the infrared spectrum, there's a tiny little peak that's too weak. That needs to dip below 80%, so we're going to ignore that. But the peak that comes after that is substantially larger. It has a range between 1600 to 1680 wave numbers. Therefore, it's a carbon-carbon double bond. It's not an amide because nitrogen would make the mass odd, so we're going to claim that this is carbon-carbon double bond. Given that information, we can now calculate that with a master charge of 120, we subtract 79 for bromine 79, we get 41 leftover atomic masses. If you subtract 24 for the 2 carbons and the C double bond C, we're left with 17. Take that 17 mass units, divide by 12, and you get 1 carbon and 5 hydrogens. That makes the molecular formula, adding up all the carbons, C3H5Br. 2 structures that are possible, and there are several possible structures, are the ones shown. Each structure has a carbon-carbon double bond, and of course contains the bromine atom.